Okay, welcome back. Part 3, we are now going to conclude Lecture 2.1 about elements and structure of the atom. Let's start with a little review of subatomic particles. I will give you a chance to read through these and answer for yourself when you pause it now. And welcome back. Okay, so maybe we can read all of these um, really carefully, or we can think first before we read and see that basically these two things in each answer are about mass and charge. And we know that protons have a positive charge and a mass of 1 AMU. So it's really a matter of finding that answer. So that says no charge, that says negative charge, that says no charge, that says negative charge. So we've just eliminated 4 possibilities. Okay, so now what's left? We have negligible mass. That's wrong. And so what's left is mass of 1, or about 1, and a charge of +1. Great. Next question. Neutrons. Let's do the same thing. Okay, it has 0 charge and 1 AMU mass, approximately 1. And there we go, right at the top. A mass of 1 AMU and no charge. And we could kind of run the same scenario here. So -1 charge is wrong, +1 is wrong, +1 is wrong, -1 is wrong, and we're left with just 2 possibilities now. So thinking about what you're looking for before you start reading through all the answers is often a good approach. You probably know what's coming next. Electrons have what? What's the charge? Minus charge. What's the mass? Negligible mass. It's obviously not 0, but it's so much smaller than the other two that we call it negligible. Okay, so again, I can take a quick look at the end of each word here, or each phrase, and no charge is wrong, -1 charge is possible, no charge is wrong, plus is wrong, plus is wrong. So now I've eliminated all but 2, and I can look at mass, and a mass of 1 AMU is wrong, and we're left with negligible mass and a -1 charge for electrons. All right, let's get on to the next topic, which is isotopes. So atoms with the same number of protons, but with different number of neutrons, are known as isotopes. Okay, so remember, the identity of an element depends on the number of protons. We're going to see here that the mass number depends on the number of protons plus neutrons. Remember, they have very close to the same mass of approximately 1 AMU. So the mass number is the sum of protons and neutrons. So even though the number of protons determines the identity of the element, the number of neutrons can be variable. Here's carbon, for example. It's atomic number 6, which you know right away means 6 protons. Carbon 12 would have 6 neutrons for a mass of 12. Carbon 13 has 7, or 6 plus 7 is 13. Carbon 14 has 8, so 8 plus 6 is 14. So we can see that the protons are always the same. Number of neutrons can be variable. All right, I revealed the answers here to these questions. So these were some think about it questions. Does the number of neutrons affect the identity of the element? And no, that is only dependent on the number of protons. Does the number of neutrons affect the charge of the atom? No, because neutrons are neutral. The charge only depends on protons and electrons. Number 3, does the number of neutrons affect the mass of the atom? Yes. The mass of the atom depends on the protons and neutrons. We can account for all of this information in a compact way with nuclear symbols. So this is a little bit different than the periodic table that we just saw before. It has the atomic symbol still. X is just a placeholder in this case. Could be K for potassium or Ca for calcium. A superscript to the left is the mass number, which is the number of protons plus neutrons. And the subscript to the left is just the number of protons. So we can see carbon from here rewritten in the nuclear symbol notation or representation. So some simple math arises from mass numbers because the mass number is the number of protons plus number of neutrons. The atomic number is the number of protons, so the mass number is the atomic number plus number of neutrons. Or we could say then the mass number minus the atomic number is equal to the number of neutrons. Let's practice. Here's a fill in the blanks in this table. So each row, enough information has been given to fill in all the rest. I've also included the equations from the last slide down here. So I want you to pause it and fill this in for yourself. And when we return, I will populate the answers. Okay, the first row is chlorine 35. So the 35 tells us that it has a mass number of 35. And the fact that it's chlorine tells us that it's atomic number 17. If it's atomic number 17, it has 17 protons. The mass number minus the number of protons is the number of neutrons, which is 18. Okay, next row. There we go. So, given here, if the atomic number is 80, then the number of protons is also 80. If the atomic number is 80, we know it's mercury. The number of neutrons plus the number of protons add up to be the mass number. The mass number, 197, is included in the name as mercury 197. Okay, and the third one. I guess I'll walk through this one. So we know the number of protons is 53. Therefore, the atomic number is also 53. If it's atomic number 53, we know that it's iodine. And it's iodine 125 because it has a mass number of 125. Now the number of neutrons would be the mass number minus number of protons, which would equal 72. Here is a question and the answers. Silicon has 3 naturally occurring isotopes: silicon 28, silicon 29, and silicon 30. What do all isotopes of silicon have in common? Well, they're all silicon, right? So they all must have the same number of protons, which is 14. And then they would also have the same number of electrons to make it neutral. So they also have 14 electrons. Question B, how are the isotopes of silicon different? They're different because they have different number of neutrons. In this case, 14, 15, and 16. C. Which isotope of silicon has the greatest mass? Silicon 30 has the greatest mass. 30 is the mass number. It's the one that has the most neutrons. Okay, so these questions here and this last question, you may notice if you look at like iodine on the periodic table, the atomic mass says 126.9. If you look up mercury, Hg, element 80, the atomic mass is 200.6, and chlorine is 35.45. So that's not the same. Where do these numbers come from? Well, these numbers come as the average atomic mass of the naturally occurring isotopes. So the periodic table shows the average atomic mass, not the atomic mass number. Okay, so we need to make sure we're clear on the differences. If we look at the isotope symbol, we might have something like chlorine 35. Periodic table says chlorine 35.453. What's going on here? Well, any given atom has to be an isotope with integer numbers of neutrons and protons. Right? So it has a mass number that has to be an integer. But all of the different isotopes are naturally occurring. So if you were to gather up, say, 100 randomly naturally occurring isotopes of a given element, like chlorine, the average mass would be 35.453. There is no such thing as a chlorine atom with a mass of 35.45. Each one, again, would be one of the isotopes, but then if you had like a handful of them, you'd have an average, right? Because every element has different numbers of isotopes, and those isotopes have natural abundances. So chlorine, for example, 24.23% is chlorine 37, and the 75.77% is chlorine 35. And so the way that you would calculate a weighted average is that given mass times the percentage plus the next given mass times its percentage, and more terms if you had more terms. Like we saw, carbon has 3 different isotopes, right? And then that would calculate to be the average atomic mass. Okay, you don't have to do any calculations like this. I just want you to know the difference between isotopes, mass numbers, and the average atomic mass that you would see on a periodic table. Okay, that's it for section 2.1. And next time we'll be looking at the groups and periods and more information of the periodic table in depth. Don't forget the post-lecture questions on Brightspace, and see you next time.